Hello, this is Paul and Dave again. This is the third talk in our series, Control Systems 101. Talk number 3 is a basic introduction to the dynamics of processes, usually referred to as process dynamics. Most control processes are electrical or electronic, mechanical, fluid flow or heat control. There are some others, such as pH control. What it is really important to understand is that all dynamic processes behave in the same way. I find it ridiculous that at university electrical, mechanical, fluid dynamics and thermodynamics are taught by different people in different disciplines in different classes. And what is worse is that each of those academic disciplines use different concepts and terminology to describe processes that behave in an identical way. Process dynamics works exactly the same for all processes, including human relationships, and in fact financial dynamics work the same way as well. What we are going to do in the next few talks is to treat the physics of each discipline as though they are all the same. Fundamentally, there are 4 types of energy, and they all follow the 2 laws of thermodynamics. The law of conservation of energy. Energy cannot be created or destroyed. It can only be converted from one form to another. And number 2, energy eventually becomes dissipated out into the universe, adding to the entropy of the universe. And I tend to think of these 4 basic types of energy in this way. So I just draw this diagram. I've got 4 types of energy. Here is a source of energy. In electrical terms, might be a battery, some kind of power supply. In mechanical terms, an engine, and so on. And then we have a sink of energy. In electrical terms, that's a resistor. It absorbs energy. In mechanical terms, this is friction. We also have kinetic energy, and I draw it there. And we have potential energy. And that's it. All types of energy in all dynamic systems, this is the sum total of how it works. Kinetic energy normally would be something like inertia. Or inductance in electrical terms. And potential energy is some kind of storage. In electrical terms, that would be a capacitor. In mechanical terms, potential energy would be contained in a spring. Now, it's important to recognise that the source of energy is passive, and that's passive too. The sink of energy is passive. A resistor in electrical terms. We call these reactive. Kinetic energy is reactive, and potential energy is reactive. When I'm teaching system dynamics to students and people I mentor, I use this. It's a chart that I've drawn myself, and I find this really convenient to explain things. So I've got the main types of processes we find in industry: electrical, mechanical translational, mechanical rotation, fluid flow and heat flow. And I've got my 4 types of energy: my source of energy, my sink of energy, my kinetic energy storage and my potential energy storage. So our source of energy, a battery, a crank, a motor, a pump for fluid flow, a heater for thermal. My sink, a resistor, a shock absorber for friction, again friction for mechanical rotation, friction of the bearings and so forth. For fluid flow, the resistance in the pipe, and for heat flow we have thermal resistance. Now, because heat is often taught by different people, they tend not to talk about resistance, they talk about conductivity. Kinetic energy storage and inductance in electrical, the mass or the inertia in mechanical. A flywheel has inertia for rotational. The fluid flow, the fluids have inertia in the pipe. And in heat flow, this is really important. Because heat does not have mass, it does not have inertia, and therefore there is no kinetic energy in heat flow. So thermal inertia does not exist. You will often hear people talk about thermal inertia. It doesn't exist. What they're referring to is this one, heat storage. So the potential energy storage in electrical, it's a capacitor. In mechanical, it's a spring or a torsion spring. For fluid flow, it's a tank, particularly a tank up on a hill, so we have potential energy. And in heat flow, the potential energy is heat storage. And once again, I repeat that when people talk about thermal inertia, they're actually referring to this, because that doesn't exist. Since we are going to head into the area of differential equations, I have another chart which is very similar, and this is the one that I use. And so we have the equations, and we'll do this again in the next talk. We have the equations for resistance, friction, fluid friction, resistance to heat flow. We have the kinetic energy storage, and these are all derivatives. So the driving force, voltage, force, pressure in a fluid are all derivatives. And the potential energy reactance is capacitance, spring tension, you have an integral, storage at altitude and heat storage, and these are all integral equations. Differential equations for kinetic energy, integral equations for potential energy. In talk number 4, we will start to set up a differential equation. Thank you for joining me, and I hope you can join me in talk number 4. The engineers in control are Dr. Paul Wilson and David Clement. You can find out more about us at www.engineersincontrol.com. Unless explicitly stated, all content in this video is original and is copyright 2022 by Dr. Paul Wilson and David Clement.